So in many of my videos, I show how to interact with tables with millions and millions of rows in order to test indexing, partitioning, and other features, especially in my introduction to database engineering course. And you guys asked me, how do you create a table with such large quantity of data? So that will be the video to essentially illustrate how to do that. I'm going to do it from scratch. I don't have anything. I'm going to use Docker to spin up a Postgres instance, create a table, create a million row, and that's it. Very short video. Let's get into it. Make sure you have Docker, and let's write this command. Let's spin up a Postgres 13. That's the latest version out there. So let's go ahead and do that. Docker run. I guess the only thing we need is the environment variable, Postgres password, and we're going to call this Postgres, just the password, Postgres password. And then I'm gonna do Postgres. That's exactly the image. But before we get the image, just give it a name. It's called PG1 because I have something called PG. And that's it. It's as simple as this. Create a database. Now I have a database. The next thing, I don't really need to expose to the port because I'm gonna SSH into the container itself and then run that command. And I'm gonna just spin up another terminal and do docker execute dash interactive terminal, and then our container name, because pg1, and then I want to execute the command as psql -u, the username is Postgres. And just like that, we are now into the Postgres command shell. The next thing we're gonna do is create a table. It's called a temp, as for temperatures. And I don't know, what are we gonna get? Like t, value t, integer. I'm gonna like create a, like assume this is an IoT populated table, right, with temperatures. So I'm gonna create a table with just one value, temperatures, and we're gonna insert a million instances of different temperatures, from 0 to, I don't know, 100, let's say. That's it, we have the table. So here's the thing, here's how you do the trick. We want to insert into temp, and that's the value we want to populate. And the trick here is to do a select, and from, I'm gonna leave this as empty here, from generate series. And this is a built-in function in Postgres, and that when you do a select from generate series, you can specify from 0 to anything really. And I'm gonna do a million here, 1 0 0 0 0 0 0. That will essentially return for you values from 0 to a million, right, in a select. But I don't really care about those values because they are very sequential. I want random values. So you're gonna call a function called random, and random are essentially fractions, right? So 0.00 whatever the values. So I'm gonna multiply by 100 to get a value from 0 to 100. And since I have an integer, this will be coursed nicely into an integer. So last thing, do a semicolon, and that's it. If you have indexes, this is gonna be, that's it, literally guys, it's done, that's it. So if I know like select t from temp, limit 10, you can see I start having values. And if I do select count star from temp, you can see I have a million rows. That's it guys. Very, very quick video, so you can populate this variable and play. You can essentially change that number to be whatever you want really, and just play with that. And now you might say, what if I have multiple fields? Just add comma and then add that. This is obviously an integer, but you can easily do the same thing to create characters with other functions, right? Convert the character, the number, into ASCII, into actual characters, and play with that. So that's essentially the core. All right, guys, that's it for me today. Very quick video. I'm going to see you in the next one. You guys stay awesome. Goodbye. All the commands, by the way, are going to be in the description, so you don't have to pause and look at this stuff.
What's going on, guys? My name is Hussein, and in this video, I want to discuss indexing, database indexing. It's a very interesting topic, and I think every backend engineer, specifically if you are involved with databases and relational databases, or any kind of databases, you need to know what indexings and how indexings work, and what is the benefit of indexing. So in this video, We'll describe what is indexing. We're going to work with indexes. We're going to work without indexing. And we're going to see how the performance differ whether you have an index or you don't have an index. So first of all, what is an index, guy? An index is a data structure that you build and you assign on top of an existing table that basically looks through your table and then tries to analyze it and summarize it so that it can create kind of shortcuts, right? The best way I can think of an index is like, if you know these, if you ever seen a secretary's handbook or phone book where you have like thick, big book and it is labeled. There's like a label color with A, B, C, D until Z, right? So the letter A starts with all the company's phone books that start with the letter A, and B start with all the B's, right? And C is all the C's. So if you want to look through find a specific company name, phone number, and you know it's like, oh, it's I don't know, it's called Zebra. So you go to the Z, right? And then you start searching there. That's the simplest thing I can think of the index, right? And basically the index, guys, are two types so far that we know of. Something called B tree and LSM trees. And I'm not gonna go through the depth of how they are constructed. This is outside the scope of this video, but essentially it's a data structure and you can look it up. It's basically allowing you to search very effectively, right? And you find quickly what you're looking for. So guys, here I have a table called employees with around 11 million rows. Okay, it's a quite large table. Okay, so I have an ID field, is integer, it's not null, and it's sequential. So every time I insert a row, I don't touch this field. It will automatically insert and increment the value. And it's also a primary key. That means unique, right? And it also has an index by default. Every primary key has an index by default, and it's a B3 index, right? So that's what I have here. And I also have a name field on this, which doesn't have an index. It's just a bunch of characters, nothing fancy. It's not really the actual name. I just spent some time generating 100 million random strings, right? So now if I, for example, do let's clear this up and do select ID from employees where ID equal 1000, I will return the thousands ID, right? That's not fancy, right? So if I do select star, I will get everything back, ID and name, and N1 is the name. So don't pay attention to the actual name. It's just a string, and that's the idea of the string here. So guys, what I want to do here is I'm going to go through steps of different queries. I'm going to show you the performance of each of these queries, right? In order to do that in Postgres, that's the database I'm using, by the way, Postgres, I'm going to do explain, analyze, which will actually explain the query that I'm going to do, and it's going to tell me how long it took, right? Which is really neat. So I'm going to do select ID from employees where ID equal, let's say 2000. Because the first one is cached. I don't want to mess up the statistics. All right, so what happened here, guys? Let's decipher what happened. It says, okay, your predicate filter, you're trying to find ID 2000. That's the employee with ID 2000. In order to find that, I didn't go through the actual table 11 million and I searched sequentially. No, I actually scanned the index, which is way faster because the index is always smaller than the actual table, because it tells you, okay, it is structured in a way so that if you search, and I'm gonna put an animation here a little bit so you can see, like if I want to find ID number 2000, it starts searching. Okay, 2000 is between 4000 and 1000, so it was okay. Let me go to this tree. So you go to another tree and then search from another between this number and this number. So until you actually find the number, right? That's how B-trees basically work, right? So now what I did, I only scanned the index, which is very, very effective, right? Heap fetches, that's another interesting thing. So it says the value that I actually queried, which is the ID, I did not have to go to the heap to fetch this information because the ID, since that's the only thing you're selecting, is in the index. So I just pulled it inline. That's called inline query. If the information is available in the index, that is the sweetest query to a database engineer. If you can put as much information as you can in the index, so that as I scan the index and you only select the ID, that is the sweetest thing you can do. So the whole thing took 0.6 millisecond, and to plan the query and to study what we go through, the fact of, oh, should we use the index or should you scan the table, is a query, is a decision, and that's called the planning time. The execution is the actual work to go and do the work. All right. So let's spice things a little bit. What I want to do here in this case, I want to select 3000 in this case, and you can see that took 0.1, 0.8. What I want to do is I'm going to change the ID 5000, and instead this time I'm going to ask for the name and compare the cost here, guys. Look how long it took. So selecting only the ID, where you know the ID, which is like a silly query, if you ask me, right? It's a little bit of a silly query because you know the ID. Why are you just selecting the ID? But it's just for science, guys. We're doing this for science. So it's pretty cool, right? It's 0.1 milliseconds, less than a millisecond, which is quite fast. However, when we actually selected the name, which is a column in the table, it is not, the column is not in the index. It is in the table. It's in the heap. It's in a different data structure, right? And in this case, it took us 2.5 milliseconds, not seconds, 2.5 milliseconds, which is quite fast, but it's still, database speak, it's a little bit slow. This is a slower query, and you guys need to understand when you execute these queries what it does really mean. Because I found the ID in the index, but I had to jump into the table row on disk, which is a different structure, by the way. The table is in a different place than the index. The index is a data structure and the table is a different data structure, right? Table is actually the heavier thing. We try to avoid going to the table as much as possible because there's 11 stinking million rows there. So we try not to touch it as much as possible, but sometimes we do. So what we did is we found the ID and then we actually try to go and seek to the disk. I mean, I have an SSD, so there is no seek. We go to the page that has this information and we retrieve it from disk. So that's another read from disk. So it's a little bit slower. It took us 2 milliseconds. And obviously, if I execute the same thing again, it's faster. Why? Because caching. Because we cache things. There's so many caches going on. SSD caches, the control SSD caches, the database caches, everyone caches. So God knows why is it faster now, right? But that's why, because I'm executing the same query. But if I change this to something else, I might not get it right, but you get the idea, right? 2 milliseconds again. All right. So now let's spice things a little bit. I'm going to do explain, analyze, select ID from employees where name is equal ZS. Let's do it. Ooh, guys, are you feeling it? You feeling it, right? That was slow. That was deeply slow. Why? Because guess what? The name column does not have an index. And that means the only way to actually search through the name, the value ZS, is to actually go one by one and do a sequential scan on employees table. That's the worst thing. It's called the full table scan. You want to avoid full table scans as much as possible. However, Postgres tries to be a little bit smarter by executing multiple threads, worker threads, and does the sequential scan on parallel, which is still good, right? So the planning took 0.83 millisecond, which is not much because, well, does this column, which is the name, equal this filter? Does this have a where clause? Does this have an index? Nope, it does not have an index. Move on. Full table scan doesn't have a choice, right? So it went through and scanned 11 million rows. Well, not necessary. Well, no, yeah, it is necessary. You have to scan the whole thing. Otherwise, how do you know that all of them, right? You have to check every single one of them, which is the slowest thing. How long did it took? It took 3 seconds. Yikesy. Yikesy. That is so slow. Yeah, so it is pretty slow, guys, to do this. Another thing that we notice all the time is I used to do this all the time without knowing. There is a command in SQL called like. Like if you don't know, hey, is ZS before and after? You just add this percentage like. This is the worst query. Why? Because it is literally has to go through all the rows and does matching in this case, right? It doesn't really matter because we don't have an index, but I'm going to show you with an index how does it do, right? So what this does is it will return all rows that have anything in the beginning, anything at the end, but has to have Z capital S small in the middle. Slow. Took 1.11 second to do all that stuff. But yeah, still 11 million row, but we had 2 workers to do the work for us. All right, guys. So what I'm going to do here is actually going to create an index on, I'm going to name it employees name on employees, and it is on the name column. So this was going to take some time to create. Why? Because guess what, guys? It is building the B-tree bitmap index on top of all the stuff, right? So it has to fetch all the 11 million rows and does all this magic to actually create the fancy index. So let's wait for it. All right, guys, we finished creating our index. So now let's try the same query that we have done, just without the like, just directly equal. So now, if I do this query, look how fast it is. Still a little bit slow, 47 millisecond, but damn, that was quick. Why? Because now we're doing a bitmap heap scan on employees, right? So we're using the actual bitmap index scan on employee's name. So we're actually scanning the employee's name index that we created. And this is way faster because we have fewer rows to work with, and we're gonna actually jump between few rows until we find exactly what we're looking for, right? And obviously, guys, the same thing applies where, hey, if you only pull the name, which is already in this index, is going to be faster than pulling the ID and the name. I'm not quite sure about this. Maybe this actually doesn't hit the heap because the index, the primary key, I know this is in MySQL, I'm not sure about Postgres, but the primary key is usually stored with every single index in other databases, right? So the name index here, the primary key will be stored. So pulling the primary key from the name index will be fast because it's right there, right, with it. So however, if you have more than other tables, then we had to go to the table structure, and that will be a little bit slow. All right, guys, so what will happen if I add like here? What do you think will happen? Back to the slow query. Back to the exact same slow query, guys. Why? Let's clear this again. Let's do something else. So we don't have hit the cache. Look at this. Back to the same slow query. Why? Because we could not scan the index. Why? This is a lot of people make this mistake. Yeah, the name column has an index, but what you did is you're not actually asking for a literal value. You're asking for an expression, and there is no index that will satisfy this expression because we cannot search the index on this expression because this is not a single value. So the planner quickly detects this, says, okay, planning time. We check, less than, oh, sorry, the filter sucks. And that's why you have to explain on your queries and see why are they actually slow. Because of this. Because look at this. We did a parallel sequential scan. Again, parallel. Not all databases do parallel scanning, by the way. But Postgres do. We had to do it. We had to go to the stinking table and scan my 11 million rows. If I have a billion rows, it's going to be even slower than that. So yeah, going through all that stuff, and I'm going to explain all this number in another videos because I don't want to make this video longer than that. I'm going to make an advanced video discussing these actual numbers. What do they mean? All that stuff. But yeah, we did a parallel scan on employees, guys. Look at that. It's so slow. We couldn't do inlining. We couldn't do any optimizations. This is an expression, obviously, so that's we had to do all that stuff. So we took a hit. We took a hit, despite us having an index, guys. Despite X having an index. So, guys, that's very quickly indexing in a nutshell. In a very, very quick video, I wanted to explain of that. Yeah, having an index does not mean that the database will always use it. It's gonna plan, and according to the planner, will decide to use the index or not. It's up to you as the engineer who's executing queries against the database to actually give hints to the database to actually use the index or not, right? This is a bad query in general. Select star is a bad query in general. Why? Because if you think about the cost to go to the actual disk and pull all the information, that is expensive, right? Really depends on how much. Like, let's say you have a blob on a column on the field or on the table. That is expensive to pull up. So if you don't need it, don't ask for it, right? And only ask for things that are absolutely there. And if you can, ask for things that are in the index, right? I'm going to talk about that in another video where there's like multi-column index where you can add other columns in the index that you're about to create. This is called inlining, where as I search my beautiful index, my neat, efficient index, I want the name, for example, right? That's a bad example, but I want the name. I am searching for the ID and I don't want the name. Oh, the name is right there. It's just literally sitting in my index. So I just pull it and retrieve it to the user. I don't have to go back on disk and find the location, seek in disk, if that's a mechanical drive, or pull the page in case of SSD, guys. All right, guys, that's it for me today. I'm going to see you in the next one. You guys stay awesome. Goodbye.
Welcome, guys. Today we're going to explain in Postgres. Get it? So there is this command in Postgres that is called explain, and it is used to retrieve information about what query plans Postgres will use for a given SQL statement. How about we jump into it? I have a beautiful table here. It has to be beautiful. If it's not beautiful, I send it back. Michael Scott. This table is called grades, and there is an ID, and there is a grade, and there's a name. So it's like a bunch of students. There's a lot of rows here, I think over 200 million. And I showed many times how to create such table and insert this much volume of rows. So there's an index on the ID, there's an index on the G, the grade, but there's no index on the name of the students. So here's what we're going to do. So we're going to execute a bunch of queries and we're going to explain them and see what Postgres will do. So let's start with explaining the select star, the worst query you can ever do. When we do that, we get this beautiful one-liner, and let's explain, let's demystify what's going on there. So the first part is usually the query plan, and this is called a sequential scan, and this is equivalent to a full table scan in other databases. Essentially what the database decided to do is like, okay, you're selecting everything and there is no filter, so I'm gonna go directly to the table, I'm gonna go directly to the heap and fetch everything. That's the sequential scan. Sometimes Postgres do a parallel sequential scan with threading. They spin up multiple threads just to do the scanning. On grades, and here is the cost. And the cost is usually has two numbers, almost has two numbers, separated by two dots. The first number and the second number. So let's explain what this means. The first number means how many milliseconds it took me to fetch the first page, right? And in this case, it took 0. Why? Because Postgres immediately went to the table and fetched the first row and immediately got results. So it cost you almost nothing to get the first result. So if you're doing some sort of a limit, right, select star from grades, well, limit 1, you're going to get a result very, very quick. This number can increase, the startup cost can increase if Postgres if the database decide to do some work before fetching, such as aggregating, such as order by, right? Things has nothing to do with actual fetching, work that precedes the actual things that you want to do. So that's, you're going to see this number. If you see this number go up, that means you're doing a lot of stuff before fetching. And this number is essentially the total amount of time that it thinks, because remember, it didn't really execute the query, right? It just tells you, hey, I think I'm going to do this, right? And this is the total amount of time, which this is in milliseconds. So it estimates that it's going to finish the whole thing in 289 seconds, essentially. And this is another estimation. This is very valuable, by the way, right? This is not an accurate number, but it gives you a quick number, approximate based on its own statistics, that this is the number of rows that it's going to fetch. That's why I always recommend, when you want to do a count and you don't really care about the actual number, like you're doing, I don't know, you're building Instagram and you're counting the number of likes, use this. Don't do select count. Select count will kill your performance. It's actually go and physically do the count on all your rows. And if you have billion rows, tough luck counting that stuff, right? That's why a lot of people use this. Explain, give me an estimate, return that. And there's the width of the row. So this is the sum of all the bytes for all the columns. And I have 3 bytes. If you sum them, you're gonna get 31 because there is text there. All right, so that's the first one. Let's spice things up a little bit. Let's do an explain, select star from grades, and we're gonna do an order by this time. We're gonna order by G, and G is the grade. What do we do? What did we get? You see that this number bumped up a little bit. It's a 0.43 millisecond. So Postgres did some work, or it is attempting to do some work before fetching the row. And that work is what? Is actually doing the sort, order by G. And it's not so bad because it did use the index that is on G to do the sorting. And guess what? The index is already sorted. So the work is very, very trivial, right? But it is work nonetheless. And that's the total number of thing. The rows in this time, this is almost the same number. It should be, better be. And then the width is also the same. Okay. Now let's spice things a little bit and do explain, select star from grades, order by name, something that has no index. And you can see there's a little bit more. In this case, Postgres says, ooh, you want me to sort by the name? The name is a column that is not indexed. So I have to go to the heap. And guess what? I'm going to pull everything in order to sort it. So it started to, first of all, it did a parallel sequence scan. Always read it from bottom going up, right? This is how we do it. Don't read it from up down. It starts from the inner thing going up, 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 up. Okay? So the parallel sequential scan on grades, it took nothing to do that because, hey, I'm going directly to the table, right? Cost nothing to go there. Again, we didn't sort yet. This is how much time we're going to take. So it's estimating that it's going to take me 200 seconds, 218 seconds. And this is the number of rows that we're going to get back, 31. Got it? All right. Now we're going to sort on the name. Look at that. Look how much it took just to get to the point to fetch something. The sorting took, man, that's a lot. That's 1,000 seconds. Yikesy, right? So you can see that this number is very critical. The first number. The second number is not so much. That's the last one, right? But the first number is everything that you need. And then obviously we plan 2 workers, so there's 2 parallel doing this thing. And since we had 2 threads, 2 processes doing the work, we gotta merge the result at the end of the day, right? And that's the total results. Obviously, we get this number, and that's the final result, and 31 width. So you see that there is more work that need to happen to get
to get to the actual thing. All right, let's play a little bit with the other stuff, guys. What I'm going to do here is I'm going to do explain select ID, not just the whole thing, just the ID from grades. Let's just try this thing. What do we get? Obviously, we get 0 cost nothing to go to the table. Well, it costs nothing to go to the table to fetch the first page. That's almost nothing, 0, right? And the rows, but look at this. Look at the width. We get 4. Why 4? 4 bytes is the result. You're asking to return only the ID, and the ID by default is an integer, and the integer is 4 bytes. By the way, careful. Don't put your primary key as just integer if you're expecting this lower table to grow beyond 2 billion. Right? That's what happened to Parler, by the way. They grow beyond 2 billion notification and then blew up their table. Right? Yeah, so there are 4 bytes in the ID. Okay, let's do explain select name from grades. You can see that the average row size is 19 because the name is text, right? And depends on the name of the students. It can go 19. They took the average and say, hey, we are expecting this to gonna be 19 bytes. So be careful with this number, especially if you're returning this across the wire to your backend application, right? The larger this number, the larger the network you're gonna take, the higher the TCP packets, right? I mean, don't put like a blob and do select star when you don't use this thing. That's why it's insulting to do a select star to the database. Only to pick one row or one column from those, right? Only select what you need. And you can see if I do, for example, the G, it's 8. That's the number of bytes in the double value. All right, let's do an how is indexing working in Postgres? Select star from grades where ID equal 10. So obviously there is a unique index on the ID here. So we're expecting this to be fast. Obviously we scanned the index and we jumped to the heap to fetch some row value, and it took us 0.43 seconds. And the total time to talk the whole thing is 8 milliseconds. Again, this is not actual times. There is another command that we're going to explain in another lesson or video where we're going to show analyze. That's the actual time token. This is just an estimation. So we did an index scan and we used the index condition, this one in this case. And you can see if we played with this a little bit and say, okay, this is a silly query, but bear with me here. So now when I do explain select ID from grades where ID equal 10, silly query, of course, because you just said ID equal 10. But you can see that now we're getting an index only scan, which is a faster one, right? That the work, we didn't even need to jump to the heap to do the work, right? So that's just another type of query. I did many videos talking about that as well. All right, guys, that was a quick video explaining explain, and this was a very, very basics of the stuff, right? Maybe I'm gonna make a few or more lessons and more videos to explain the analyze, explain the buffers, explain the shared hits and other stuff as well. Let's keep this video short and sweet. Gonna see you in the next one. You guys stay awesome. Goodbye. What's going on, guys? My name is Hussein, and I want to take a few minutes to explain the difference between a sequential table scan, an index scan, and a bitmap index scan, which is something specific to Postgres. But regardless, it's very, very clever, and I want to take a few minutes to explain the difference between the three. You're more familiar with the sequential table scan as full table scan, but that's just a Postgres terminology. How about we jump into it and play with this a little bit? So I have a table here called grades, and it has an ID, which is a primary key, and it's a auto increment, a serial. I have a primary key, which is an index. I have an index on the ID field. It's just a 1, 2, 3 incremental value. I have a name, which not index or anything like that. I have a grade field, G, which indicate this is, think about this like a grades of students, right? And G is a value between 0 and 100. And there is an index on the grade field that includes as a non-key value also the ID field, which is pretty something we talked about in many videos, right? So now what I want to do here is explain many aspects of how can I query this table to retrieve certain data. And pay attention to this. I'm going to explain
do an explain, because I don't really interested in the result. I just want to know what Postgres is about to do when I want to execute this query. So I'm going to select name, the name of the student, from the grades where ID is equal 1,000, right? Where there is a specific ID. And the moment you do that, you can see that the Postgres is going to use an index scan using the grades primary key, which is the ID, and then provide the values using the index condition on the index. That's the ID equal 1,000. And it's going to pull, we know that it's going to pull one value, right? And that explains it, why we have one row. Once we pull that row, now the index is responsible to go back to the table to bring the name field. Why? Because the name is part of the heap. It's part of the table, which is part of the heap, right? Which is another data structure. The index is a different data structure. But now, if I do this, for example, so it's like less than, let's say, 100. So I'm bringing around 99 value. So Postgres still decided to do an index scan. So what happened here? Let's go through exactly what happened. So we brought 98 rows in this case. What Postgres did, it says, okay, you want any student that has an ID less than 100, which is kind of a silly query if you think about it. What the database decides says, okay, I'm going to use the index to do an index scan on the ID index, and then go scan one by one and find anything that is less than 100, right? And that's very quick to do in a B-tree, especially that the Postgres kind of have a clue of how many rows it's going to get back, right? It says, okay, I want anything that's 100. Anything that's greater than 100, just toss it away. And so it knows that it's going to get values 99 or less because maybe something was deleted. And as a result, it used an index. And for each value that it finds the page where that row exists and goes back to the heap to pull that page, which kind of have one or more rows, and then pulls that value. And this is called random access. So for 99, it went to the page, went to the heap, pulled the row. It did that for 98, for all the rows. Okay, so this is called random access. So you can see that this can get slow if you have a lot of rows. So let's go do something ridiculous. By the way, I have around 50 million rows in this table. So I'm going to do ID greater than 100. Postgres actually is smart enough to know, okay, I expect that this table, this query is going to be insane. So look what that database did here. It says, okay, ID is greater than 100. I have, what is the maximum ID? It has them statistics, right? And I calculate this as a statistic by doing analyze grades. And when you do analyze grades, it will calculate some statistic on the table. It says, okay, this table has like 50 million and this guy wants anything that's greater than 100. That's going to bring 50 million rows back. Is that 50 million? Sorry, 5 million, right? I forgot how many rows I have in this table. So 5 million. So it's going to bring all of those puppies back. Well, wait a second. Scanning the index, and every time I find a row in the index that satisfies ID greater than 100, which guess what? Almost all the rows will satisfy that, except the 100 that is less than the 100, right? I'm going to go and jump. That is extremely expensive to jump back and do a random access. So the Postgres decided to do a sequential scan. What was that? Sequential scan. And says, you know what? Let me just jump to the table and do a sequential scan on the table itself. It's way cheaper to do a sequential scan, full table scan on the table itself. Okay, and pull the results. Now we have two things. If Postgres saw that you have few rows, it's going to use an index scan. If it thought that it's going to have a lot of rows, it's going to say, you know what, it's way cheaper for me to do a sequential scan on the table because I'm going to go there anyway. I don't want to jump, read the index, and then read the table. That's expensive, right? So if I'm reading the table and the index all the time, might as well just go and read the table fully, right? That's easier. So now the compromise between the two is when you have a case where you don't have a lot of rows. You don't have a lot of rows so that justifies a full table scan, but you have quite enough that it's actually efficient to use the index. So what Postgres does is actually does a bitmap scan. Let's go on an example of a bitmap scan. A bitmap scan is when you do something a little bit slightly less ridiculous. Like, give me the grades that are greater than 95, right? It's like Postgres doesn't really know how much, but it knows it's a lot. But since there's an index on G, which is the grades, it's worth doing an index scan. But doing an index scan and jumping to the table all the time for every value I find is expensive. So it's going to do instead something called the bitmap index scan. Let's talk about that a little bit. So the bitmap index scan, and you're going to see something, some graphics that I put on the video here, where Postgres is going to build a bitmap, and it's basically an array of bits, and the values represent the page number. So bit number 0 is page number 0, bit number 1 is page number 1, and so on. Okay, until the total number of pages that is in this relation or this table, grades in this case. Okay, so what the Postgres will do, it will do a scan, a bitmap scan on G, and it says, well, you know what? When I find a value that satisfies this condition, I'm going to do an index scan. This is a normal index scan, but when I find something, I'm not going to jump directly to the table when I find a page. No. I'm going to set a bit on that bitmap. So for example, let's say I found a row, right? And that row belongs to page number 9. So I'm going to go to that bitmap and set bit number 9 as 1. That means, hey, by the way, I found a row that on page 9, and then goes and grew all of the index. It scans the whole index. You have a beautiful bitmap that you can use to jump once to the heap table and pull all these pages. Okay, so that's what we're gonna do right here. Now we're gonna do a bitmap heap scan. So using the number of pages that I know exactly to fetch, I need to jump to the heap once and fetch all those pages. Okay, and when I fetch all those pages, guess what? Every page is gonna have one or more row, right? That's how Postgres stores things. Guess what? Some of those rows will not satisfy the G greater than 995 criteria. So the Postgres does a recheck on the condition, only to filter out the rows that has been filtered, and drops the rows that have been filtered. In this case, we were lucky that the exact number of rows actually fit exactly in the pages, right? So that's a bitmap index scan. So this is very, very interesting, guys. So let's spice things up a little bit. With a bitmap and scan. So the beauty of the bitmap index scan is you can scan multiple indexes or indices, if you're from the UK. You can scan multiple indexes, build those bitmaps, add them together, and then get one beautiful bitmap and then jump to the heap. Let's take an example. I'm going to do an explain where grade is greater than 95 and ID is less than, I don't know, 10,000. When I do that, look what happened here. ID has an index and G has an index. So what Postgres did, it did an index scan, a bitmap index scan on G, and calculated that beautiful bitmap that we talked about, and did another bitmap scan on grades primary key, which is the ID field, and then now I have two bitmap. What it did, it just ANDed them. You know how smart this is, guys? By ANDing them, any page that exists in one and doesn't exist in the other, I don't have to visit it, because 100% that row is not going to satisfy my criteria. This is genius. So all of a sudden, instead of having 9,000 rows and whatever this thing, 20,000 rows, you're only going to fetch 394 rows. Beautiful. And then once we have this beautiful final thing, you go to the heap, we do a bitmap heap scan this time with this final result, ANDed result, and then go and do a recheck. Why? Because you have to do a recheck. Because you're fetching some pages, some rows on those pages that you're fetching might not satisfy your criteria. So you're doing a recheck again on those things. That's not so expensive, because once you fetch a page, you get those rows for free in memory, hot, right? In the shared memory, to be specific. All right, guys. So that was table scan, full table scan, sequential scan, index scan, and bitmap index scan, and bitmap heap scan. Hope you enjoyed this video. I'm gonna see you on the next one. You guys stay awesome. Goodbye.
Hey guys, in this lecture I'd like to discuss the difference between key versus non-key column indexes. In a nutshell, when you want to create an index in Postgres or really any other database, you specify a field or more than one field to index to create that B tree on top of, right? And that key will be used for searching purposes. And when you do a search on that index, the database planner will use that index and search for that, and the entries that found in the index will contain row pointers to point back to the table to fetch the actual rows. So where we have more than one field there. All right. Non-key indexes are abilities. I don't believe it exists in all databases, but it definitely exists in Postgres, where you can effectively create an index and create non-key, include some columns inside the index, not to search for, but to include. So in this case, if you select, like you created an index on the grades field, right? And you can optionally include other fields in the index, like the ID. So now if you select and search by the grade and you want to select the ID, the index doesn't have to go to the table because everything is literally in the index. Let's explain this and see the performance benefits that we get in all of them. Let's jump into it. So I'm going to include in this lecture SQL file that will be creating the students table here. And the student table, I deliberately added kind of a big table with a lot of fields to demonstrate the expense of doing this stuff. And we have a primary key here, and this table actually have 50 million records. Let's do a select count star from students. Boom. Yep, 50 million rows. Make sure if you're using Docker to run this container with plenty of shared memory, and do a vacuum so that we update all the stuff, make sure the visibility map is up to date so we get the optimal query, right? Now that being said, right, I don't have any indexes here, right? So what we're gonna do is do an let's do this query: explain, analyze, explain, so we can explain the query, analyze, so it tell us how long it took. I'm gonna do select ID and grade. I want all the students that got results between 90 and 95, right? So from students, where grade is greater than, let's say, 80 and less than, and G is less than 95, right? So you can effectively select this range of grades, right, of these students. And I'm going to order by G in a descending manner so that the largest grade goes first and all the way down. Obviously, this is a little bit of an expensive query because you're going to select a lot of rows. Usually this is not recommended, but we're showing the capabilities here. So if I do that, it's going to take a long time, and it's going to tell us how long. All right, so the query is finished, and it took, let's see, it took 21 seconds, 22 seconds actually to finish. And look at what it does. It had to do a sort. Why? Because we're doing order by grade, right? Because I want to sort these grades that I results, right? It didn't have any index on the G field that I'm searching because I don't have any index there. So it had to do a parallel sequential scan, sure, spun up multiple processes to do the hit the disk directly, fetching. Look at all this beautiful stuff that is merged from disk. It's so slow. We're going directly to the data file on the table and pulling pages, all the junk, right? There's so much junk there. There's grades that are 10, 12, 13, and we have to filter this out, right? Remove and filter this out. And look at this. This is what's painful. Rows removed by filter, right? So we pulled pages and we had to discard what, 14 million? Is that what? 14 million rows are useless. So we pulled pages with rows, but They are just basically filled with stuff that we don't want, and that's what an index helps for, effectively. So, and you can do something like more realistic. It's like, I just want the first 1,000 students, and this should run faster, but not always. In a sequential scan, this is not nearly necessary to. It's gonna take faster because it doesn't know. It needs to search and until it gets the results, right? So yeah, it took 17 seconds, so 3 seconds faster to pull only 1,000 students. All right, so that's obviously slow. So the first thing we need to do is actually create an index. How do we do that? Create index GIDX on students G. So now this is the fields. I want to create an index on G so that we can order by the G and filter on the G, because that's what we're doing. We better be a little bit effective when it comes to that stuff. And that's because the indexes are by default ordered. And we love, in databases, we love things that are already ordered for us because it's predictable instead of randomness. Randomness is chaos. That was deep. All right, so we have an index. Let's execute my beautiful query again. Let's execute the original one. So what we'll do now, we're querying by G, greater than 80, less than 95, order by G. That will use the index. We can't guarantee it because the planner has a mind of its own, but let's say they're gonna decide to use the index to search for things. But look at what we asked for. We asked for the ID. Where is the ID? Well, the ID is actually in two places. The ID is on another index because the primary key, and it is also in the heap as another field. So this has to go to the table again to pull the IDs. So you will use the index, it should use the index to pull whatever it needs to pull, right? Find the candidate rows and then jump to the table to pull the IDs of the students. Let's see how fast it is. So it didn't help much. We have an index and we still took 16 glorious seconds to fetch all of the information. Well, still better than 21, right? But still slow. Why? And main reason is really we did an index scan backward. You might say, why backward? Because we said order by descending, so which is at the end. So we did a search for 80. We did this condition on the index and we found one entry, and since this is a p+3, we're gonna release. It's all nicely tucked in together, all the values. That's the beauty of the b+3s, right? So all the values are next to each other. We found all the candidate rows. It's actually this many rows that we found. It took us 42 milliseconds. This is not really in millisecond, but this is the cost. 42 cost, whatever this unit is, to find the first one, and 15.8 to find the last one, right? So that's like equivalent to a millisecond, but some people say that it's not really millisecond. So yeah, it is slow, still slow. Saying that's a ridiculous query because nobody's gonna fetch all these rows, right? I just want 1,000 students. Well, it is much faster this time, and that makes sense because it took like 0.5 milliseconds. So bear in mind that we won't be always this lucky to take 0.45, right? Because usually this query are hitting the cache, the operating system cache, because we did execute a lot of queries before, right? So if I do like something like analyze and then I did buffers, right? You can notice that, look at this, shared hit 20. That means all the things that we queried are cached. That is why it's so fast, right? That's why a lot of you ask me, good question, Hussein, you did this query and it's so slow, and you did it again so fast. Why? Because the operating system does all the magic of caching all the time. So we need to trick the operating system a little bit. So let's just a little bit change the equation. Let's do this. Give me all the students from, I don't know, 10 to 20. So this should look at that. We're doing a little bit of reads now. We did hit the index, not the index. We hit the IO. We hit the disk. We no longer do a shared hit, right? Still, we did a few pages hit, but it's better. So that's why it got up to 6 milliseconds, right? But still, there's a lot of pages that are cached, right? So that's why it's absolutely blazing fast, right? We need to find a way. So if I change this to 10,000, it took 25 milliseconds. I bet that if I remove this limit, it's going to be faster now this time. So a little bit better, right? Look at this. We got 90,000 IO to disk. We went to disk 90,000 times effectively, and we took 11 seconds to do that. Yikesy, right? So we know why. We understand how the system works because it's just an index scan, and the reason is because you're selecting the ID, which we have to go to the table for, and that's most of the cost, the IO cost to go to the table, while we already living in the index. So the idea is, how can we do a pure index only scan? Let's drop this index that we just created, and we're going to create a beautiful new index that is on the G, but we're going to include a non-key index here, non-key column, sorry. G index on students G, but we're going to include ID. Why? Because that's a very common execution path that we're doing. That's where you, as a backend engineer, you really need to think, like, what columns are you selecting? And based on those columns, you create your indexes effectively. Let's create that. So it finished. It took a little bit longer, and that makes sense because, well, the index is larger now because we're including more stuff in it. The ID field, which is in 32-bit, I believe, right? And has to pull these values and store it. So obviously it's going to take more time. But what happened if I execute my beautiful query now? Let's do just the normal one. Look at that. It took only 4 seconds. And we had to go to the disk. You might say, Hussein, you just said that this is an index-only scan, right? In an index-only scan, which is nicely done here, right? It did say index-only scan. So in this index-only scan, we didn't have to go to the heap at all. Heap fishes equals 0. So this row, you see this line if only when it's in an index only scan. If you see heap fishes more than 0, that means we had to go to the heap for any reason, right? One reason is that you didn't run vacuum, the visibility map is out of sync, right? You made some changes, you updated the rows, so you have to do a vacuum in order to update all this stuff. So we did a read. For some reason we had to dirty 3 pages. I'm not sure why, right? But again, even selects in Postgres sometimes does write all the time, right? To update these visibility things, the hint bits as they call them. So it took 4 seconds, and then I bet if you execute it again, and this is, again, guys, this is the entire thing, huh? I'm not doing any limits here. I pulled everything that's between 10 and 20, right? And it took 1 second this time because guess what? We cached more, we hit more pages, right? And we only had to go to the IO 602 times. And you might say, why are we going to the disk? I thought that we were just reading the index. Guys, the index is still on disk, right? It's a very large index, and we have to hit the IO because it lives on the disk. It will be very beautiful if we can fit the index entirely in memory. That's the ideal situation. But unfortunately, that's not always the case. I have an old MacBook with 16 GB RAM. It's a Docker container that is not really running with bare bad defaults, so it won't really. And I think I have only 1 GB shared memory shared with this guy. with Postgres. But it's always important to run, by the way, always run vacuum verbose, right? And on the students table, let's just run it. This will tell us like if there's anything wrong. If you got any errors here and you have to do verbose, it will tell you that, oh, by the way, there is some bad things. I have to remove all these dead tables, dead rows. So you guys have, if you want to replicate this lecture, you have to run vacuum verbose students, right? Or even just vacuum verbose full all together, right? This will help you update all the pages, the visibility map, anything. It will basically treat Postgres as if it's a production ready to be read, right? And the moment you start updating fields and adding values and inserting rows, then you have to do vacuum again. I mean, vacuum is auto run by default, but it's always good to run this. So you can see that we got much better performance. Let's do a limit now. This is even a 0.5, right? It's really fast. So guys, at the end of the day, you've seen the performance. It's not really huge if you think about it. It really depends on your use case. The larger the table, the better non-key indexes will be, right? But keep in mind that the index grow larger if you include stuff in it. And if you include stuff in it, it can't fit in memory. And if it can't fit in memory, it will be put on disk. And if it put on disk, that's a read, that we have to read the index from the disk to do the queries. So learn about this. You don't have to implement it. Just know that it exists. Put it in your back pocket as a tool. I'm going to see you in the next one. Hope you enjoyed this. All the code, the SQL stuff is going to be included in the lecture resources. Gonna see you in the next one. Goodbye.
What's going on, guys? My name is Hussein, and in today's video we're gonna explain what's the difference between an index scan and an index only scan. How about we jump into it? So I have here a Postgres database, and I have pSQL, and I have a beautiful table here with no indexing or anything like that, right? So I have an ID, a grade, and a name of the students. Look at a bunch of students table. Very simple table, right? So what I want to select here, for example, if I select the name where from grades where ID equals 7, you can see that this particular person's ID 7 is named Hussein. And if I do like select star from grades where ID equals 7, you can see that the grade is 81. It's all boring stuff. So what we're going to look at as database engineer, we're interested in what the database did to fetch this row. So we do explain, analyze, and we do the same query again. Select name from grades where ID is equal 7. And since there are no indexing on the predicate on ID equals 7, the database decided to do the only thing it knows, which were parallel sequence scan, which is the table scan, which goes to the table itself and just literally one by one search every single row, pulls it, and then look, is it ID 7? Nope. Let's look at the second one. Is it ID 7? Nope. Until it finds the ID 7, right? And it took 400 milliseconds to do that, and it returns one row essentially. That's how we should look here, right? So that's what it did. So now we know how to create an index on this ID because it's powerful stuff. So if I do create index ID index on grades, and let's say on the ID field, right? So this way we're going to create a B3 index so that searching is a little bit faster. And that's a completely different structure from the table we talked about. This table that has, I think, 10 million students, right? So now we just created another table, given that ID, that beautiful tree, so that is way better in searching. We can search that in that index in a very different way than we're searching a huge table. So let's do the same exact thing on this table. And just like that, we went from 400 millisecond to 1 millisecond in the index. And look at this. It says index scan. I want to differentiate between index scan and index only scan. We're going to come to that next. It is an index scan Because, yeah, we use the index, which is called ID index, to search for ID 7, and we quickly found out that. However, what's not mentioned here is we had to go back to the table to actually fetch the value name, because that's what we're asking for. We're asking for the name of the student, right? And the name of the student is not in the index. The only value in the index are the IDs. And we found the ID, but we had to go back to the table. So that table structure we talked about, the one we scanned earlier, it's there. And we had to go back using the reference, the row reference of the table, to jump back to that table, fetch that ID number 7, and fetch that whole row. That includes the name, the grade, and pretty much any other columns as well in the table itself. Beautiful stuff. So if I change this query a little bit, guys, and I asked only for the ID, does the database need to go to the table? The answer is no, because the ID is right there. Obviously, this is a silly query, right? Because the value is 7. But look at this. It says now index only scan. That is powerful. It says index only scan because it did not have to go to the table. And that, if you can execute queries in your application so that they are index only scan, you hit the jackpots. Index scan are great, are nice, but index only scans, ooh, they're the beautiful. However, this is a silly query. How do we make this a little bit more useful? Here's what I'm going to do, guys. There's something called non-key columns, where as we create indexes, and I created, and I actually made a video about this topic. Check out here. But we can drop our index. Let's go ahead and drop our index, and we're gonna recreate our index IDX on grades on the ID. However, while we creating that, I know that most of my queries, when I query for the ID, are asking for example, the grade, or for the name. I barely ask for the grade. I only ask for the name, for example. So I'm going to actually include the name field in this index. This is called a non-key column. This is called a key column. This is what we're going to search against. This is what we're going to fetch from the index, right? So it's not going to be using this for optimization or searching. This is just what we're going to store in the index so we can pull the information very efficiently. So now if I do this, I'm going to create a brand new index, same exact index. What the difference is, we now pulled the values from the entire table, the name, into the index, just the name column. So now if I do the same exact query, and I'm not going to ask for the ID, I'm going to ask for the name. What do you think is going to say? That the planner is going to say index only scan. Beautiful. Why? Because we asked the database, hey, find me ID number 7, student with ID number 7, but go back and give me the name. The database is, oh, wait a second, I'm not going to go back to the table, that huge 10 million scary table. I'm staying right there. The name is actually in me, in the index. So there you go. Just return it. So that's why it took much faster to execute. Beautiful, powerful stuff. So now if I change this from name to grade, that's no longer an index only scan. It's an index scan. Different. Why? The grade is not available in the index. So we had to go back to the table and fetch the row, and we took the hit in order to fetch the grade. So guys, this is what I wanted to explain in this video, guys. And pay attention to the cost of these things, guys, because as we work more with a large index, and including non-key columns in the index, can actually increase the size of the index. And if you increase the size of an index, that could be really bad, right? Because the bigger the index, the slower it gets to query it, because you had to fetch more and more pages to get into the things that you're looking for. So just be careful of that. just have an idea of what your query looks like, what your structure looks like. This is very useful thing, guys. That's it for me today. That was the sequential scan, index scan, and index only scan. Hope you like this video. Give it a like, subscribe for more backend engineering stuff. I'm gonna see you on the next one. You guys stay awesome. Goodbye.